Welcome back. We are to the second section in chapter 6. Today we're going to be talking about one-to-one functions first and then inverse functions. This is one of the more abstract lessons that we're going to be doing. But we need this foundation so when we get to logarithms, it makes a little bit more sense. We're going to start with some conditional statements and one-to-one functions. A conditional statement is also called an if-then statement. If P, then Q. Is what the arrow means. A conditional statement is equivalent to its contrapositive, it's called. So if not Q, then not P. So for example, for our conditional statement, if it is raining, then there are clouds in the sky. And our contrapositive to that would be, if there are no clouds in the sky, then it is not raining. We're going to use similar logic to what we're doing here. A one-to-one function, a function is one-to-one if for every element y in the range, there exists exactly one element x in the domain such that y equals f of x. And by looking at a graph of a function, you can tell it is one-to-one, or how can you tell that it's one-to-one? And the answer is the horizontal line test. I hope we all know that horizontal lines go this way. There are two ways to prove that a function is one-to-one. This is much higher up mathematics than you'll need, but this is the formal way to show that something is one-to-one. You assume that f of a equals f of b, and then you have to prove that a equals b. Or you can assume that a doesn't equal b, then you can show that f of a does not equal b. We're not going to do that. We're going to use the horizontal line test, which is not particularly difficult. All right, prove the function f of x equals 3x plus 5 is a one-to-one function. So let's go ahead and graph it. So 1, 2, 3, 4, 5, 1, 2, 3. And so our graph is going to be up here at 5, 1, 2, 3, 4, 5, then up 3 over 1. So we end up with a straight line, y equals mx plus b. And we all know what a straight line looks like, but the big thing here is that when I draw a horizontal line, now you might remember the vertical line test, that's to determine if something is a function or not with vertical lines. But this time we are drawing horizontal lines, and as long as it doesn't cross it more than one time, we're good to go. So there it crosses once, we're good. Every horizontal line can cross the graph no more than once. Therefore, f of x equals 3x plus 5 is, and I'm going to show you the fancy way to do one-to-one, one-to-one. That's right. All right. Now, to be clear, in higher mathematics, sometimes the entire function is not one-to-one. And what we can do is we can limit its domain so that we only are dealing with a one-to-one portion of it. So for example, if we have a graph that looks like this, what we can do is we can limit the domain so that we are only dealing with from here to here. Then you can see every horizontal line is going to cross no more than once, but the whole graph itself is not one-to-one, but we would need to limit its domain to do that. All right, page 2. Part 2, verifying functions are inverses and graphing inverse functions. All right. A function has an inverse function if and only if it is a one-to-one function. Now, we now have what's called an if and only if statement. If you remember the if-then statements, it's usually one directional, but in this case, if then is the same as then if. You can switch them out. These are better, and actually in math harder to prove. It actually requires 2 proofs. All right, meaning we can only have inverse functions of one-to-one functions. And so let's continue here. What is the inverse function, inverse operation to adding? Meaning, what is the opposite of adding? That's subtracting. And what's the opposite of multiplying? It's dividing. Meaning they cancel one another out. And we know this because we've used it numerous times, even in this class we have. Many, many times. Inverse operations undo one another. That's a great way of putting that. The functions f and g are inverses if and only, here's another if and only if statement. When you composite the two functions, they cancel each other out and you just get x. And the composite doesn't matter. You can have the f first, then the g, or vice versa, as long as we're within the domains of the innermost function. So let's start there. Let's verify that these two, now this is a straight line. We have a slope and a y-intercept, and we just saw that these are 1-to-1. And this is also a straight line. So these are definitely 1-to-1. And we're going to verify that these are inverse functions. So I'm going to composite f composite g of x. And if we play our cards right, the answer should just be x. That means that they're inverses of one another. So this is going to be f of x minus 2 over 3. So I'm going to replace that x with this here. So this will be 3 times x minus 2 over 3 plus 2. And I'm going to notice that the 3's reduced, which gives us x minus 2 plus 2. That is just x. Yay, they're inverses. So that's how you verify that. You can composite. And you could do it the other way. I could do g composite f, and they would cancel out as well. I'm not going to bother with that, although you're welcome to do so. All right, example 5. If f and g are inverse functions and f equals, and we have these 3 points, then g is going to be, and here's a key factor with inverse functions, the domain of one is the range of the other, and I say that down here somewhere. So this becomes 4, 1. See, it's exactly backwards, exactly opposite there. And here, it's going to be 8, 5. And here it's going to be 10, 7. All right, notation. So here's the notation that we use for inverse function. It looks like f to the negative first power. That is not what that means. In fact, I make a big deal about that here. This does not mean this. Okay, these two literally mean that they are inverses of one another. They are opposites of one another. And you can see the notation on a basic calculator. You can see above the sin button, actually pronounced sine, it is sine to the negative first, it looks like. That's actually inverse sine, inverse cosine, inverse tangent. You can see the negative one exponent looking thing, but it does not mean an exponent. When you graph f inverse and f on the same graph, they are symmetric about the line y equals x, which can be helpful if you're graphing both. And to find an inverse function of a continuous function, make sure that f is 1-to-1. Then you switch out the x and y's, and we'll do an example of that in just a moment. Solve for y if possible. The ones that we're doing will be. Replace y with f inverse of x. Again, that's not to the negative first. That's f inverse of x. If you really want to verify it, you can composite the two together, and they should both equal x. And since x and y are interchanged, so the domain of f is same as the range of f inverse, and the domain of f inverse is the same as the range of f. So in that, you can see that there because the x and y swap out. All right, let's find some inverses. Start with part A. So first thing I'm going to do is rewrite it as y equals 7x minus 2. And as the direction said, we're going to swap out the x and y's. And then we're going to solve for y. Change y equals x plus 2 over 7. And the last part is replace the y with f inverse. That is how you find the inverse of a function. Now, again, if you want to verify that, you can take that and plug it, this whole thing, and plug it into where x is. You can see the 7s will cancel out, the 2 and the 2 would cancel out, just like the previous example that we did. All right, part B. So I'm going to rewrite it. And we have an extra thing where x is going to have to be less than or equal to -7. We'll talk more about that here in just a moment. So let's go ahead and swap out the x's and y's. And now I need to solve for y. So y plus 7 is going to equal plus or minus the square root of x. Now here is where we run into a problem. This plus or minus means that it does not pass the horizontal line test, but because we have a restriction here, that'll help us. So if x has to be less than or equal to -7, and since I swapped out the x's and y's, this now means for us that y has to be less than or equal to -7. So for that to be less than or equal to -7, I have to choose the negative portion of this. So f inverse of x is going to be -7 minus root x, so that we can fulfill that there. Let's do this. Part C, y equals root x minus 3. And we're going to assume that x is bigger than or equal to 3. Swap out the x and y's. X squared plus 3. So f inverse of x is x squared plus 3. And we are, again, limited on our domain. So since x has to be bigger than or equal to 3, y has to be bigger than or equal to 3, but you can see y will be always bigger than or equal to 3. Part D. Y equals x over 2x plus 1. Swap out the x's and y's. I'm going to multiply through by the LCD. So 2y plus 1 times x gives me 2xy plus x equals y. They cancel out here. And now I'm going to gather the x terms to one side. In fact, I'm just going to move, since I already have a y here, I'm going to move this to the right. So x equals y minus 2xy. And on the right side, I'm going to factor out a y. Here, I'm going to divide both sides. So y is going to be x over 1 minus 2x. That last step. Here we are, the inverse function of f. Again, a little abstract, a little out there, but not particularly difficult, I don't think.